Welcome to The Explainer. If you're a focused learner trying to wrap your head around complex technical breakthroughs without all the fluff, well, you are in exactly the right place. Today, we're tackling a massive, honestly pretty frustrating challenge in modern machine learning, scaling graph neural networks, or GNNs, on modern hardware. We're going to break down a fascinating paper called On Efficient Scaling of GNNs via I/O-Aware Layers Implementations. And trust me, by the end of this explainer, you're going to understand exactly why your GNNs are running so slow, and more importantly, the brilliant architectural tricks researchers are using to actually fix it.
Okay, let's dive into this with a question that honestly plagues a lot of machine learning engineers. Why don't faster GPUs make GNNs proportionally faster? I mean, we're constantly throwing more and more compute at our networks, right? We buy the latest, greatest hardware, we expect these massive speedups, but with GNNs, the performance just refuses to scale. It's this central paradox. You've got all this incredible processing power just sitting there, literally twiddling its thumbs. But why? Well, to figure that out, we've got to look at what modern hardware is actually built to do versus what GNNs force it to do. Just look at the massive disparity between compute and memory on modern hardware. Take an A100 GPU, for example. You've got a compute throughput hitting somewhere around 312 teraflops. That is huge. But your high bandwidth memory, your HBM, is only moving data at about 2 terabytes per second. This is what we call the roofline model. Because GNNs operate on graphs, their memory access is highly sparse and super irregular. They're basically constantly jumping all over the place in memory just to find neighbor nodes. And because of this completely erratic behavior, they slam into a memory wall long before they ever get close to maximizing the computational limits of the GPU. They're just completely starved for data.
The researchers actually summarize this perfectly. They note that many implementations prioritize operator generality while under-optimizing data movement and intermediate materialization, making performance increasingly dominated by memory traffic. Basically, popular frameworks like Deep Graph Library or PyTorch Geometric, they want to stay flexible, which makes sense. But in doing so, they under-optimize data movement. They end up creating this massive, totally unnecessary memory traffic by constantly materializing intermediate edge data. They're writing temporary calculations out to that super slow global memory and then reading it right back in again. In a system that's already starved for memory, that is a total performance killer. So how do we build a solution? Well, the researchers propose a taxonomy. They essentially chunk the entire GNN universe into 3 specific operator families. Why? Because each family interacts with the hardware differently and needs its own unique I/O-aware optimizations. First up, we've got SPI-MM-based convolutions, like your standard graph convolutional networks. Second, there are reduction-based aggregations. These handle things like max or min pooling. And finally, the really complex attention-based layers, like graph transformers and GAT-V2. By splitting the problem up this way, we can systematically attack the specific memory bottlenecks of each one.
And how exactly do we attack them? The answer is I/O-aware implementations. This right here is our core solution strategy for the rest of the explainer. We really need a fundamental mindset shift. We have to completely stop thinking about more compute and start obsessing over less data movement. The whole goal is to explicitly reduce traffic between that slow high bandwidth memory and the ultra-fast on-chip SRAM. And we pull this off by avoiding writing those intermediate steps out to memory in the first place and by maximizing the reuse of data while it's already sitting right there on the chip.
Section 1. Fixing GNN load imbalance, the reduction problem. You know, real-world graphs almost never have a nice even distribution of connections. They have what we call heavy-tailed degree distributions. Think about social networks, a few massive influencers and millions of regular users. If we process every single node exactly the same way, those few massive nodes are going to completely stall the GPU. So the solution is degree-aware partitioning. For light nodes with just a few connections, we use a simple feature parallel kernel. It accesses memory in a smooth, coalesced way. But for heavy nodes, we definitely can't do that. Instead, we use 2D edge tiling. We essentially chunk that massive list of neighbors into smaller blocks and process them all in parallel across different GPU thread blocks. It stops the heavy nodes from holding the rest of the computation hostage. But of course, chunking creates a brand new problem. How do you actually combine the results from all those parallel chunks without causing a massive synchronization traffic jam? So the crucial point is this completely brilliant 3-step 64-bit packing trick. To find a global minimum across all these chunks, they first map the floating point values to order-preserving integers. Then they pack that value and its source node index into a single 64-bit word. Finally, they use a single atomic min operation. This updates both the minimum value and its location simultaneously. It allows all those parallel chunks to merge flawlessly without any complex, super slow cross-block synchronization. Honestly, it's just a highly elegant hardware-level hack. Section 2. Fusing attention for speed, the GAP v2 and transformer fix. If you've ever worked with graph transformers or GAT v2, you already know they are notoriously memory hungry. And that's because standard vanilla frameworks explicitly materialize intermediate messages for every single edge. They generate this massive activation footprint that scales with the number of edges, heads, and dimensions, an O of m times h times d footprint. It's huge. The I/O-aware fix for this is called fused CSR attention. Instead of computing scores, saving them all to memory, loading them back to normalize, saving them again, and loading them to aggregate, we just fuse the whole thing. We compute the score, normalize it, and aggregate the value in a single streaming pass right over the neighbors. We completely eliminate those explicit edge tensors, which just slashes high bandwidth memory traffic. Now, the real magic making that single pass possible is something called online softmax. See, normally you need all the attention scores at once to calculate the softmax denominator. But here, the GPU maintains running statistics right inside its ultra-fast local registers. As every new neighbor gets processed, the algorithm incrementally rescales the output accumulator. If that sounds a bit familiar, it's actually the exact same fundamental concept behind flash attention, the trick used to speed up large language models, but applied here to the crazy, irregular structure of graph data. We're calculating completely correct attention weights on the fly, without ever needing to touch global memory. Even with that fusion, though, we're still mostly relying on standard CUDA scalar cores. Why? Because graph data is just so scattered. But if we want to truly unlock the GPU's full potential, we really need to fire up the tensor cores, which are purpose-built for dense matrix multiplication. This brings us to the weighted block sparse, or WSB layout. By taking local graph neighborhoods and packing them into fixed-size 16 by 16 tiles, we effectively force that sparse, scattered data into a dense format. So for graphs that have locally dense pockets of connections, this WSB layout finally lets GNNs tap into the massive mathematical horsepower of GPU tensor cores. It's a real game changer. Section 3. The graph reordering nuance. Now, graph reordering, basically renumbering nodes to improve cache locality, sounds like an absolute magical fix on paper, but the actual benefits are highly nuanced. Just look at the massive variance across these different datasets. And this brilliantly illustrates that reordering truly helps only when your kernel relies on gather-dominated mappings on dense graphs. You can see the OGBN products dataset spiking there. But then look over at the highly sparse City Roads L network. The impact is literally hovering right around zero. If your graph is too sparse, the per-node working set is just so small that reordering does almost nothing at all. It is definitely not a silver bullet. Section 4. Speed and memory games, the climax. All right, we've covered the theory and the architecture. Now let's look at the actual payoff. Just let this number sink in for a second. 76x. That is the peak memory reduction achieved during the forward and backward passes of a GATV2 attention layer on the Tullikers 2 dataset. 76 times less memory. By fusing the kernel and eliminating the materialization of those intermediate edge tensors, the researchers didn't just trim the memory footprint, they absolutely obliterated it. Practically speaking, this means you can train significantly larger graphs on the exact same GPU without suddenly running out of memory. And it's not just about saving memory, it's about pure, unadulterated speed. 10x. That's the top-end latency speed it measured for reduction kernels. Remember that degree-aware tiling we talked about earlier? The trick that stops a few massively connected nodes from completely stalling the GPU? Well, this proves that when you intelligently map the workload to the hardware based on the graph's actual topology, you can achieve a full order of magnitude speedup in processing time. That's huge. Finally, what about those standard spam-based layers, like your basic graph convolutional networks? Well, even there, the researchers achieved up to an 8x speedup. The trick? It turns out NVIDIA's proprietary QSparse library is incredibly fast on its own, but the standard frameworks often introduce a ton of setup overhead. By simply caching the QSparse metadata and caching a transposed adjacency matrix for the backward pass, you can totally bypass those framework bottlenecks, and doing that unlocks massive latency improvements with surprisingly little effort. All of this incredible optimization brings us to a really provocative final thought. We've seen today that the absolute best approach, whether that's CSR fused streaming, degree-aware tiling, or Tensor Core WSB layouts, depends entirely on the real-time statistics of your specific graph. So the next frontier isn't just about writing faster kernels. Will adaptive runtime autotuners soon make all this manual memory tuning in GNNs completely obsolete? Imagine a system that automatically analyzes your graph's density and degree skew on the fly, and then instantly routes the math through the perfect hardware path. That is the future of GNN acceleration. Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.